Hello everyone, my name is Mingbin Huang and I'm glad to present our work ArcGraph, a Acyclic architecture relation predictor for task-transferable neural architecture search. Neural architecture search methods have the potential to democratize deep learning and reduce costly human labor in designing neural networks. By automatically searching for optimal architectures, many NAS methods have discovered models exceeding human-designed ones on various tasks. Beyond seeking solutions for a single task, there are surging interest in transferring network design knowledge across multiple tasks under cases where networks for multiple tasks are needed. Current predictor-based NAS methods model NAS as a regression problem, which can be hard to solve because of the complex model space. We propose ArcGraph, a task-transferable NAS method, by formulating NAS from a novel perspective, a graph ordering problem, and solve this problem by training a pairwise relation predictor. Here is the overview of our framework. There are two stages in our framework. In the first stage, we'll train the pairwise relation predictor on a source task, and fine-tune the pairwise relation predictor on the target task, and get the architecture relation graph by treating candidate architectures as nodes and their pairwise relationships as edges. In the second stage, we endow the architecture relation graph a partial order by computing the maximum weighted acyclic subgraph and hence get the final ordering. The details will be introduced later. Before digging into the pairwise relation predictor training, we first want to talk about how to identify a task when transferring knowledge across tasks. A task's nature can be quantified by the neural network's weights when trained on this task. When a pre-trained model is fine-tuned on a task, it is actually adding some perturbation to the network's weights, and we can measure the average KL divergence between the original output distribution and the perturbed one. This will generate a fixed data-dependent embedding for a given task. Some previous work on NAS have suggested using randomly initialized task embedding when transferring network design knowledge. We'll compare the results in the table. As we can see, using our task embedding leads to a better and more stable knowledge transfer across tasks. In the pairwise relation predictor training stage, we propose to use pairwise relation predictor instead of a regression-based one, because when training a pairwise relation predictor, we can generate n-square samples for training by pairwise comparison among n given ground truth accuracy of architectures. This leads to higher accuracy of our predictor that takes two architectures as input and produce a probability indicating which architecture performs better in a given task. After we finish the training and fine-tuning of the pairwise relation predictor, we can get the predicted pairwise relation on the target task and construct the architecture relation graph on the target task. In order to find the top performing architecture, we want to find a subgraph that defines a partial order, where edges exist with high confidence and there are no cycles in the subgraph. This leads to our definition of maximum weighted acyclic subgraph. After finding an approximate solution to MWAS problem, we can get the approximated ranking of the whole model space and hence evaluate the top ones. Here is our results on TransNAS Bench 101, a benchmark that provides architecture performance across 7 vision domains, including classification, regression, pixel-level prediction, and self-supervised tasks. Our method's prediction also results in a higher Kendall rank coefficient and Pearson correlation coefficient and less budgets. It can find top 0.16% and top 0.29% architectures on 2 search spaces and save at least 37.5% training samples. Here we project the model space to 2-dimensional space, and shallower color means better performance. Our method's predictions are closer to the global optimum and better average ranking. Thank you for your listening.